Good day everyone. I am pleased to present example 5.7 on behalf of our team. Today we'll be investigating system stability using the Routh-Hurwitz criterion, a powerful analytical tool that allows us to determine stability without actually solving for the roots. Good day everyone. I am pleased to present example 5.7 on behalf of our team. Today we'll be investigating system stability using the Routh-Hurwitz criterion, a powerful analytical tool that allows us to determine stability without actually solving for the roots of the characteristic equation. Our specific problem is to investigate the stability of a seed order system with the characteristic equation s to the seed plus s to the fifth plus 2s to the fourth plus 2s cubed plus 3s cubed plus s plus 5 equals 0.
I'll explain how we set up the first two rows of the root array. The root array is organized with rows labeled by descending powers of s exponent 6 at the top down to x exponent 0 at the bottom. The first two rows are filled directly from the polynomial coefficients using a specific pattern. And so for the top row, s exponent 5, we start with a sub 6, which is 1, skip a sub 5, take a sub 4, which is 2, skip a sub 3, take a sub 2, which is 3. And then we skip a sub 1 and take a sub 0, which is 5. And so the s exponent sixth row has 1, 2, 3, and 5. Moving on to the second row, labeled s exponent 5, we take the coefficients we skipped. So we have a sub 5, which is 1, a sub 3, which is 2, a sub 1, which is also 1. So the x exponent fifth row also contains 1, 2, and 1. So this is what we have so far. The first two rows have now been filled with the values from our polynomial coefficients, and so the remaining 5 rows will be calculated using the Routh formula.
Thank you. I'll compute the s to the fourth row. To calculate the elements in any row below the first two, we use the Routh formula. This formula is based on a 2 by 2 determinant. The pattern is we take the two rows directly above the ones we are computing. Form a small 2 by 2 matrix using column 1 and the column we want. Calculate its determinant, negate it, and divide by the first element of the previous row. Let me demonstrate this with the first element of the s to the fourth row. So in the first calculation box, we use rows to the sixth and we use rows s to the sixth and s to the fifth. We need column 1, so we form this matrix. That is the top row 1 and 2 from s to the sixth, columns 1 and 2. Bottom row 1 and 2 from s to the fifth, columns 1 and 2. The determinant is 1 times 2 minus 1 times 2, which equals 2 minus 2, which eventually equals 0. So we negate this, and the negative of 0 is still 0. We then divide by 1, which is the first element of the s to the fifth row. 0 divided by 1 equals 0. So the first element would then be 0. Moving on to the second calculation. For the second element, we use column 3 instead. So that's the matrix. Top row is 1 and 3. For the matrix, top row is 1 and 3. And then the bottom row is 1 and 1. The determinant would be 1 times 1 minus 1 times 3, which equals to 1 minus 3, which equals to the negative 2. Negating the answer, we get negative of 2 to be a positive 2. We then divide by 1, which then gives us a result of 2. So moving on to the final result, we then have the row s to the fourth as 0, 2. And this row in the first column creates a special case that the next person would be addressing in the next slide. Thank you.
We have a problem. The first element of row S to the fourth is 0. And this is a problematic because the Routh formula requires us to divide by the first element of our previous row. We cannot divide by 0. The standard solution is to replace the 0 with a very small positive number called epsilon. Okay, it's denoted by the Greek letter. If you know your tree, air in tree, that's like a 3 but turned. Yeah, you can see it on our screen. We think of epsilon as approaching 0 from the positive side. Okay, so our S to the fourth row becomes epsilon 2. Now we can proceed to calculate row S cubed. For the first element of S cubed, we use rows S to the sixth and S to the fourth. With our matrix, our top row is 1 and 2. The bottom row is epsilon and that's epsilon, and two determinants is 1 times 2 minus epsilon times 2 equals 2 minus 2 epsilon. Okay, now we negate the negative 2 minus 2 epsilon equals to 2 epsilon minus 2 divided by epsilon. Simplifying, this equals 2 epsilon divided by epsilon minus 2 divided by epsilon. As epsilon approaches 0, 2 epsilon divided by epsilon approaches 2 divided by epsilon. Okay, and 2 divided by epsilon, when epsilon is tiny and positive, is a large negative number. So the first element of our S cubed is negative 2 over epsilon, which is large and negative. So for the second element, matrix 1 and 1 epsilon with 0 determinant. 1 times 0 minus epsilon times 1 equals negative epsilon. Negate and divide by epsilon, the positive epsilon over epsilon equals 1. So our row S cubed is negative 2 over epsilon 1.
So I'll be computing row S squared. So this calculation uses the two rows above, that is S to the fourth and then S squared. Yes. So our rows are S to the fourth, epsilon, S to the fourth, that is epsilon and 2, and then S squared, that is 2 epsilon minus 2 over epsilon and 1, right? So since 2 epsilon minus 2 simplifies to negative 2, we can write S squared as negative 2 over epsilon and 1, right? So for the first element of x squared, right, the matrix uses columns 1 and 2 from these two rows. From the top one, that's epsilon and 2, and then the bottom one, that's negative 2 over epsilon and 1, right? So now we'll have to compute our determinant. So computing our determinant, we have epsilon times 1 minus negative 2 over epsilon times 2. This will then give us epsilon minus negative 4 over epsilon, which equals epsilon, right? And then plus 4 over epsilon. So now we move on to divide this entire expression by the first element of row S cubed, right, which is negative 2 over epsilon. So now we have epsilon plus 4 over epsilon divided by negative 2 over epsilon. For us to divide by a fraction, we would have to multiply its reciprocal. So now we have epsilon plus 4 over epsilon times negative epsilon over 2, right? And therefore, this would lead us to find epsilon times negative epsilon over 2 plus 4 over epsilon times negative epsilon over 2. This would give us negative epsilon squared over 2 minus 4 over 2, which then also gives us negative epsilon squared over 2 minus 2. Right. So as epsilon approaches 0, epsilon squared is even tinier. So from our expression, we can see that as epsilon approaches 0, epsilon squared is even tinier than epsilon, right? So negative epsilon squared over 2 approaches 0. Therefore, this expression approaches negative 2. This expression, that is negative epsilon squared over 2, approaches negative 2. Right. But then I think there is something we overlooked. We would have to negate our determinant first. So therefore, we would then have our final expression to be positive 2 as epsilon approaches 0. We can also recalculate this by using the proper Routh formula with negation. That's it having the negative sign. And our result would simplify the whole expression to positive 2 as epsilon approaches 0. So rho s squared is now 2, 1, 2 and 1. The second element is 1. Carried over from the second element is 1, and it is carried over from the s squared rule since there is no other third rule. Thank you.
So I'll be taking us through computing for row S1. We'll be using rows S cubed and row S squared. So for row S cubed, we have it to be negative 2 over epsilon and S squared to be 2 and 1. So for the first element of S to the first, that's S1, we have our matrix being negative 2 over epsilon and 1 from S cubed. And we have 2 and 1 from S squared. So for the determinant, we know that it's going to be negative 2 over epsilon times 1 minus 2 times 1. This gives us negative 2 over epsilon minus 2. So we go ahead to negate because there's a negative sign, which gives us positive 2 over epsilon plus 2. So we divide what we have by the first element of S squared, which is 2. So 2 over epsilon plus 2 divided by 2 equals 1 over epsilon plus 1. As epsilon approaches 0 from the positive side, 1 over epsilon approaches positive infinity. The positive 1 becomes negligible compared to this positive infinity. Hence, we have rho S1 to the first being 1 over epsilon, where this is a very large positive number.
So for the S rule in the complete table, we first use our S squared to be 2, 1. So from S to the first, you can see 1 over epsilon. So for the first element, S to 0, the matrix 2 and 1, that's from the S squared, and 1 over the epsilon, and 0, that's from the S to the first. There is no second column, as you can see. The determinant is going to be 2 times 0 minus 1 over the epsilon times 1, which is going to be equal to 0. 1 over epsilon, which is equal to negative 1 over the epsilon. 0 minus the negative 1 over the epsilon, which will give you negative 1 over the epsilon. That's the, if you negate the positive 1 over the epsilon, you first divide the first element of S to the first, which is 1 over epsilon. Then you divide by 1 over epsilon, then we are going to definitely get 1. So the rule S to the 0 is going to be 1. When you are computing the root array with all the 7 rows holding, from S to the 6, that's 1, 2, 3, 5, 5S to the 5th one, are getting 1, 2, 1s to the fourth. The epsilon 2s is going to be cubed. The negative 2 over epsilon. Then we have 1s squared, which is 2. And we have 1s to the first one, as you can see, is going to be 1 over epsilon s to the 0, which is 1. Now when the array is complete,
Going to first column extraction. Let me extract just the first column and determine the sign of each element as epsilon approaches 0 from the positive side. S to the 6th, which is 1, this is positive. S to the 5th, which is 1, this is positive. S to the 4th epsilon. As epsilon approaches 0 from positive, this is also positive, but very small, but yet positive. S cubed, which is negative 2 over epsilon, as shown on my screen. As epsilon gets smaller, this becomes more and more negative. So this is the negative squared, which is also 2. This is positive. S to the first 1 over epsilon. As epsilon gets smaller, this becomes more and more positive. So this is positive. S to the 0, which is 1. This is also positive. So point to sign change analysis. Now, let's count sign changes as we go down the column, which is showing on my screen. From S6 to S5, which is positive to positive. No change from S5 to S4. Positive to positive. No change from S4 to S3. Positive to negative. Yes, this is a sign change, which is count 1 from S3 to S2. Negative to positive. Yes, this is a sign change, which is count 2 from S2 to S1, which is also positive to positive. No change from S1 to S0, positive to positive, which is also no change. So pointing to results as shown on my screen. Total number of sign changes in first column, which is 2. This is the critical results according to the Routh-Hurwitz criterion. 2 sign changes means 2 roots in the right half plane.
I'll interpret what the sign changes in our results mean. The fundamental principle of the Routh-Hurwitz criterion is straightforward. That is, the number of sign changes in the first column of the root array equals the number of roots with positive real part, which means the roots located in the right half of the S-plane. Now, the roots in the right half of the S-plane are problematic because they correspond to unstable modes in our system response, and even a single right half plane root makes the entire system unstable. We found 2 sign changes in our result, from positive to negative and negative to positive, as shown here in the root array. Therefore, our characteristic equation has exactly 2 roots in the right half plane, making 2 of the roots unstable. Let's put this in perspective. Since our characteristic equation is of the 6th order, as you can see here, s is to the degree of 6, right? We know that these 2 roots are in the right half plane. What that means is that the remaining 4 roots will be in the left half plane, making them stable. Now, one might think that because majority of the roots are in the left half plane and the left half plane represents stability, the total system is going to be stable. But this is untrue, because even a single right half plane root makes the entire system unstable. Therefore, we can conclude that our total system is unstable since 2 of our roots are in the right half plane. Thank you very much.
Alright, so based on our Routh-Hurwitz analysis, the verdict is quite clear. Our system is unstable. So looking at our characteristic equation, which is s raised to the power 6 plus s raised to the power 5 plus 2s to the power 4 plus 2s cubed plus 3s squared plus s plus 5 equals 0, has 2 roots with positive real parts. So in control systems, we can derive some conclusions that if this were a feedback control system, it would exhibit unbounded growth. Small disturbances would grow exponentially over time, and the system would be unsuitable for practical control applications without modification. So, in summary of what we've accomplished today, firstly, we can say that we applied the Routh-Hurwitz stability criterion to a 6th order characteristic equation. Secondly, we encountered and properly handled a special case, which is a 0 appearing in the first column, which we replaced with a very small number epsilon. And then thirdly, we completed the entire Routh array calculation, working through rows involving epsilon and taking the appropriate limits. Fourthly, we counted 2 sign changes in our first column. And then finally, we concluded that the system has 2 unstable roots in the right half plane, making it an unstable system. So for our key takeaways, we can say that the Routh-Hurwitz criterion is a very powerful tool that helps us to determine the stability without having to solve the characteristic equation necessarily. And for higher order systems like this 6th order example that we have, solving directly will be very difficult. So the Routh-Hurwitz method has given us an answer in a very systematic way. The special case of the 0 in the first column is a common occurrence, and it is handled by the very small number that we introduced, epsilon. The criterion provides not just a yes or no answer to stability, but tells us exactly how many roots make the system unstable, and other crucial information for control system design. Thank you very much for your attention, and we will be willing to answer any questions that you have concerning the Routh-Hurwitz criterion or for this specific example.